Greetings. I think we're ready to get started. Can you hear me? Yes, good.
Yes.
I'm Nancy Mead
Yeah.
with Carnegie Mellon University. I've been interested in software security for a long time, and so I'd like to welcome you to this session that I know we are all going to enjoy on software security. A couple of housekeeping details. If you're not speaking, please mute your microphone so that we don't have any distractions. And if you could put your comments and questions in the chat session, that would be wonderful. And we will get back to them about halfway through. We have 6 papers being presented. Each paper will have 5 minutes for presentation. And then at the end, we should have a really enjoyable discussion session. So with that, there's one other small detail. I am fairly certain that I will mispronounce some of the names of the speakers. So please do feel free to reintroduce yourself with the correct pronunciation after I introduce you. So our first paper is Deep Learning-Based Vulnerability Detection. Are we there yet? And our presenter is Jan Grubo, otherwise known as Robin Ding. So take it away. You can unmute your microphone and share your screen.
Okay, can you hear me? Thank you very much, Nancy, for introducing me. I mean, your pronunciation is pretty good. Let me share my screen. Can you see my screen?
Yes, it's perfect.
Okay, thank you. Okay, hi, my name is Xiangru Ding. Today I'm going to present our paper, Deep Learning-Based Vulnerability Detection. Are we there yet? In this paper, we investigated current deep learning-based vulnerability detection tools and their limitations when applied to real-world scenario. We systematically identified, categorized, and studied the limitations and proposed some intuitive solutions at the end. Vulnerabilities are flaws in the code that create potential risks that compromise software security. To detect these security issues, human experts have concluded many vulnerable patterns and integrated such knowledge into static analyzers. In recent years, deep learning models have been introduced to this field as it is able to leverage the huge amount of training data to capture more complicated vulnerable patterns and recognize them from the wild with more flexibilities. In this paper, we studied the limitation of existing deep learning-based approaches from 2 main categories, data sets and the models. As we have realized, vulnerable programs are quite rare comparing to normal benign programs, and an effective detector should be able to pinpoint such rare cases out of many thousands of programs. Because of such rareness, it is quite challenging to collect enough samples for the deep learning models to be trained on. To combat many existing tools are trained on synthetic or semi-synthetic vulnerable code where the vulnerable patterns are mostly simple and the vulnerability is often well isolated. And these tools have empirically proven that the deep learning models are quite effective at detecting such issues. However, the real vulnerable patterns are much more obscure and complex, and detecting such patterns is more challenging for the models trained with synthetic samples. Researchers also try to extract real-world vulnerabilities from open source projects to train the model more efficiently capture these challenging patterns. Existing works make their data sets to be roughly balanced. However, our study shows that such models are struggling when applied to the real-world super imbalanced scenario. To address the limitations of the existing data sets, we design a new prototype of data collection. First, we identify the project issues, flaws. We also make sure that the issue is resolved and there is a patch attached to the issue. We annotate all the functions that are unchanged as non-vulnerable. For the functions that are changed, we annotate the version before the patch as vulnerable and the version after as non-vulnerable. Finally, review ends up with a real-world and super imbalanced vulnerability data set. Now, let's move on to the issues of existing models. The most intuitive design is to apply token-based model to consume the source code, as humans regard programs as a sequence of tokens at the first glance. Therefore, the early works are proposing to represent code as sequence and use recurrent or convolutional neural network to learn the vulnerable patterns. While these token-based models make some correct predictions in such a binary classification task, they cannot correctly highlight the vulnerable signals. When we poke the model a little bit, we see that the model thinks that the red portion is responsible for the vulnerabilities. This means even when the model is doing the correct thing, it is doing it for a wrong reason and picking up the wrong signals from the data will make the model brittle. We hypothesize that using a sequence-based models lacks the capacity to analyze the code structures and the data dependencies that play an important role in detecting vulnerabilities. Therefore, we study using graph neural networks, or GNN, to learn such vulnerable signals. And we provided details in the paper that GNN indeed works better than the token-based models. While we are celebrating the improvement that GNN brings us in the binary classification task, we notice that model is not well separating the code representation based on their labels. As you can see, programs of distinct classes are combined closely as a whole. Therefore, we propose to apply representation learning together with the cross-entropy loss to better learn the separability of vulnerable programs. To conclude, we design Review, a graph-based tool to detect the vulnerabilities in real-world software projects. Given training data, we extract code property graph containing all structure relationships between code components. From the code property graph, we extract initial code features for every node. Then we use graph neural network to learn the node features from the graph structure, and we aggregate those to generate graph level features. Given a collection of such graph level features, we do resampling to reduce the imbalance bias and train our tool Review. Here is the summary of our paper, and thanks for your attention.
Very good. Thank you very much. We will immediately go on to the next paper, although we may have the presenter not here, in which case we'll skip and see if we can come back. The next paper should be an empirical study on implicit constraints in smart contract static analysis. Do we have a speaker here? Okay, we'll go on to the next paper, which is ROP Gen toward robust code authorship attribution via automatic coding style transformation. And the speaker is Jen Li.
Yeah, I'm here.
Who I see on the
Can you
screen,
hear
but
me?
I don't see him or her in
Can you
person
hear
yet.
me? Yeah, can you hear me?
I can hear you.
Okay, thank you. I share my screen.
Jen, are you here with us?
Yeah.
Haha, okay.
Can you see my screen?
And we
It's
can see
okay?
your screen share.
Okay, thank you. Hello, everyone. My name is Jen Li. I'm a associate professor at Science in China. This work was done when I was a postdoc at the University of Texas at San Antonio. The work
But
was
we're not
cooperated.
hearing you, even though your microphone appears to be active.
You can't hear me?
I can actually hear you.
Okay. This work was cooperated with Professor Tian Chen, Ms. Zhou, and Professor Xu. First of all, what is source code authorship attribution?
Can the other folks hear Jen?
Yeah. You can't hear me? I'm sorry.
I can
can't
hear you.
me?
I
Oh.
can hear you. How about you, Nancy?
Nancy, can you
Professor,
hear me?
Now I can.
can you hear me? Professor Nancy? Is it okay now?
In the meantime, we've lost the screen share. Uh-huh.
Professor, can you hear me?
Hi, Nancy. I think everybody can hear except for you, potentially.
Well,
So
that's
maybe
really
we could-
strange. All right, let me just look at this. Well, in that case, go on and don't worry about it. I'll figure it out.
Okay.
And move on. Can I move on to the next page?
Yes, I think you can continue, and then I'll let Nancy know when you're done.
Oh, okay. Thank you. First of all, what is source code authorship attribution? Here is the source code example. The question is, who is the author? Does Bob written that? The authorship attribute method can answer this. But what if Bob has not written that? So the program here may be an adversary example. There are two attacks against single authorship attribution: exploiting adversary examples and coding style imitation or hiding. The state of the art is the current code authorship attribution methods are vulnerable to these attacks. If the goal of the attacker is to misattribute P prime to Eric, it's a targeted attack or coding style imitation attack. If the goal of the attacker is to misattribute P prime to anyone but Bob, it's an untargeted attack or coding style hiding attack. Existing attack methods are manual, semi-automatic, or automatic, but not applicable to deep learning-based methods. So we focus on enhancing the robustness of deep learning-based authorship attribution methods. We propose two new attacks, which exploit automatic coding style imitation and hiding, and we propose an innovative framework called ROPGen. The key idea of ROPGen is to incorporate data augmentation and gradient augmentation to learn about robust coding style patterns. We focus on C, C++, and Java programs, and we systemize 23 coding style attributes according to the following three requirements. We propose two attacks. The first attack is automatic coding style imitation attack. There are 4 steps. We extract the coding style attribute values from the target author programs and the attacker program, and synthesize coding style attribute values, identify coding style attributes for code transformation, and finally conduct code transformations to imitate the target author. The second attack is automatic coding style hiding attack. We use imitation attacks by choosing a target author with the highest misattribution probability. There are 5 steps. Steps 1, 2, 3, and 5 are similar to 4 is to select the author for transformation with the highest misattribution probability. We propose the ROPGen framework to improve the robustness of deep learning-based methods. There are 2 paths: data augmentation and gradient augmentation. For data augmentation, we extract the training set by coding style imitation and generate manipulated programs by coding style perturbation. For gradient augmentation, we train a robust deep learning model. There are 5 sub-steps. We train a full-flat network and several subnetworks. When the 5 substep iterates and When it converges, we can obtain a robust trained model. All experiments focus on 3 research questions. The first research question is about robustness of existing methods. The results show that existing deep learning-based methods are far from robust against known and new attacks. For the second research question is about the robustness of JobGen. JobGen-enabled methods are substantially more robust than the original deep learning-based methods. The third research question is about comparing adversarial training methods. The result shows that JobGen substantially outperforms the other adversarial training methods for attacks by both exploiting adversarial examples and coding style imitation and hiding. Here are some takeaways. We systemized 23 semantics preserving coding style attributes and transformations, and we proposed 2 automatic attacks, and we proposed JobGen framework to enhance the robustness of deep learning models. That's all my presentation. Thank you for attention.
Thank you, Jen. Nancy, we're all set.
Great. Thank you very much. I enjoyed looking at the slides, even though I didn't hear anything. And I hope that's just a temporary problem. Our next paper is REMAS, Reducing Defect Inheritance in Transfer Learning via Relevant Model Slicing. And our presenter is Shiqi Zhang.
Okay, thanks, Professor. Hello, everyone. I am Ziqi Zhang from Peking University. Next, I will introduce our paper, REMAS, Reducing Defect Inheritance in Transfer Learning via Relevant Model Slicing. Is the screen sharing stopped? Hello?
We cut out. You could try resharing the screen.
Okay. So it is my connection problem. How about now?
Looks good.
Okay, I will continue. Software reuse is a common practice for the software developers. For example, third-party libraries are widely used by the developers. DNN model is a new generation of software, and the model reuse is also called transfer learning. In transfer learning, a company collects a large-scale dataset, trains a general DNN model, and updates the model to the internet. Then an individual developer downloads the model, prepares a small-scale dataset, and fine-tunes the model. The final model is a specialized DNN that only performs certain tasks. The general DNN is often called the teacher model, and the specialized DNN is the student. However, despite the great convenience of the software reuse, the vulnerability propagation is one of the most concerning issues. One example is the famous Heartbleed bug in the OpenSSL library. Due to the wide usage of OpenSSL, the Heartbleed bug may threat all SSL-based communication applications. Similar to traditional software reuse, transfer learning may inherit defects. The teacher may inevitably contain the errors. Thus, the fine-tuned student model inherits the similar defects. With 2 major defects, causative defects such as DNN backdoor and exploratory defects such as adversarial vulnerability. For the adversarial vulnerability, the attacker downloads the teacher model, analyzes the model, and finds the bug of the teacher DNN. These bugs may be inherited by the student and be used to attack the student application. For the backdoor, the attacker can intentionally poison the training data set. Then, the trained teacher model contains some special backdoor. After the developer fine-tunes the student model, the backdoor remains and threats the applications. We surveyed prior literature and summarized several defects. The experimental results show that the defect inheritance rate ranges from 52% to 97%, meaning that this is a real threat in DNA model reuse. We illustrate the defender score with this Venn diagram. For conventional transfer learning, the teacher and the student share much knowledge. We aim to compress the shared knowledge so that it contains mostly the student-related knowledge and excludes the unrelated knowledge. To reduce the defect inheritance problem, we propose to use relevant model slicing, which is also called ReMOS. ReMOS is motivated from relevant slicing, which computes the statements that have the potential to influence the target variable. The figure shows an example. This code snippet contains a potential defect. If the input B is 0, a divide by 0 error may occur at line 8. Directly reusing this code snippet will inherit this defect. But if we know the input domain is less than 1, we can select the criteria and slice the relevant parts. The defective statement is excluded by the relevant slice. Similar to relevant slicing for programs, the relevant slicing for DNN aims to extract the weight subset that is more relevant to the student dataset. As the teacher model contains general knowledge, it is possible to select different weight subset for different student tasks, thus minimizing the possible inheritable knowledge. ReMOS consists of 4 stages. Coverage frequency profiling uses the student dataset to compute the weight relevance to the student task. Ordinal score computation computes a weight score based on the static teacher's information and the dynamic student's information. The first step identifies the relevant slices, and the last step uses the student dataset to fine-tune the slice. Our evaluation implemented various defects. For example, inspired from prior work on DNA testing, we evaluated ReMOS on neuron coverage-guided adversarial vulnerabilities. The results show that ReMOS eliminates averagely 63% of the inherited defects. To summarize, in this paper, we found that the popular DNA model reuse faces defect inheritance problem, like traditional software reuse. We identified 2 possible inheritable defects, adversarial vulnerability and DNA backdoor. The defect inheritance problem can be mitigated by reusing the relevant slice instead of the whole model. We propose ReMOS, a relevant model slicing technique that can mitigate over 60% of the CV inherited defects and 40% of the NLP inherited defects. Thank you.
Very much. Our next paper is ModX, binary level partial imported third-party library detection through program modularization and semantic matching. And our
thank you,
speaker,
Professor.
Thank you. You can take over.
Hello everyone. Today we are talking about ModX, a binary level partially imported third-party library detection via program modularization and semantic matching. My name is Yang Can. With the rapid development of commercial software, third-party library reuse has become popular. However, the massive usage of the uncontrolled libraries will result in issues. Existing feature-based matching approaches have 2 limitations. First, they embedded the features from the entire third-party library. And second, compiler settings change the features of binary codes, which makes existing algorithms not robust. Here is two examples. Challenge 1, the bytecode differs, which means the assembly code are very different. And second, the syntactic features. Here is a string literal was removed by the developer. And hence, we propose ModeX, a framework which utilizes a novel modelization technique to decompose the binary and library into modules and semantically match them to detect either fully or partially imported third-party libraries. It consists of two phases. One is binary modelization, and the second is the TPL detection. A traditional, classic solution to the modelization is the Givon-Newman and the following methods. Firstly, they defined a metric to measure the modularity quality, and then they choose the best modelization which achieves the best MQ score over the whole network. Hence, there are three key points of our modelization in binary programs. The design of MQ, the dividing policy, and the efficiency is important. We changed the original MQ matrix from measuring the indirect graph to direct graph, since the function calls have directions. Also, we adjust the function volume by the number of statements in the function, so that when we modelize the program, we can able to begin with this heavy-weighted function to avoid generating modules with only small utility functions. Based on the proposed modularity quality score, we use fast unfolding method to group functions. It works by calculating delta Q of each merge step to know where is the best MQ and where to stop the merging. However, to make generated modules more intuitive, we add in two biases to guide the modelization process. The first bias is function entry limit bias. We would like the model to have limited entries to ensure the single and encaptured functionality. The second bias is the locality bias, which is based on a heuristic. We added bias to let the algorithm consider the nearer function first, rather than to reach functions that are very far away. After modelizing the program and the third-party libraries, we propose the similarity measurement algorithm to match the modules based on the syntactic features, the graph features, and the function similarities to detect the third-party library in the program. The function similarity is calculated by many function matching tools, which here is Gemini. Here is an example about modules generated by human expert. It is generated from source code file. You can see there are isolated functions in the model, and the functionality about here is string parsing is not complete. And here is the module generated by our tool. The functions are very relevant. You can tell from the function names and no isolated functions, and the functionality is more complete. We also select 7 metrics from different aspects to evaluate the quality of generated modules. Table shows that compared to existing binary program modelization approaches, our tool outperforms other tools. We evaluate our tools on 2 sets of binaries. One is built automatically by the Nix script, and the other is built manually. In experiments, most of binary libraries are partially imported, since the modern linker will only link the used portion of the third-party library by default. The semantic model matching and partial library detection capture ability enables our ModeX to outperform other works. Here is the performance evaluation. In modelization time, ModeX costs less time than BCD, which is another binary level modelization tool. However, in detection time, since other methods only use syntactic features which can be indexed quickly, they have better performance than ModeX. Also, ModeX has the best malware violation detection accuracy. And we show that the modelization technique has the potential to aid the security analysis by providing modules which contain more vulnerability and are worthy to be further studied. You can see in the table 8, the OpenSSL project, only 3% of modules with about 12% functions have over 70% CVEs. Here is the conclusion, and thank you for listening.
Well, thank you very much. That's very interesting, along with the other papers. The last paper in this session is large-scale security measurements on the Android firmware ecosystem. And I believe this speaker is Jin Sang Hu.
Yeah, can you hear me?
Great, we can hear you.
Okay. Let me share my screen.
Now we just need the screen share.
Okay. Can you see my slide?
Yes.
Okay. Yeah. Hello everyone, I'm Qin Sheng Ho, and the topic I'm sharing is a large-scale security measurement on the Android firmware ecosystem. This is a joint work by Shandong University, Qianxin Technology Research Institute, and Tsinghua University. And firstly, here is an overview of our method. We have collected more than 6,000 room images from more than 150 vendors and extract 440,000 APK files. In addition, we also collected more than 600 CVE vulnerabilities. Our measurement analysis focuses on two aspects: the official patch, which mainly measures the patch delay and patch missing, and the pre-install app, including the actual impact of known vulnerabilities and the discovery of unknown vulnerabilities. The first is the measurement result of the patch delay. From our measurement, we found that about 24% of images have patch delay issues, with the average delay time greater than 3 months. The worst case is from Oppo, and the patch delay time is as long as 40 months. In addition, we also found that 45% of Xiaomi firmware have patch delay issues. For patch missing, we found that about 7% of the firmware has missing patches. The worst case is also from Oppo, which missed 46 security patches in the firmware of Oppo. About 20% of the firmware has missing patches, and the average number is 1.5. From this, we can answer our question 1 and question 2. For question 1, the security patch delay is widespread in Android phones. It means that the updated images of many vendors focus on the feature update, not the security update. For question 2, the claims of vendor patching may not always be reliable. The possible reason is that vendors do not have sufficient testing time or cannot bear the maintenance cost. Next is the measurement of the actual impact of known vulnerabilities in pre-installed apps. In this table, we can see that these 5 apps are all associated with undisclosed vendors. Therefore, the actual impact of pre-installed app vulnerabilities far exceeds the disclosed impact scope. The last column of the table shows the compared time range of the associated firmware. These 5 apps were all disclosed with security vulnerabilities in 2019. However, we can see that after the vulnerabilities were disclosed, there are still many firmware introduced the vulnerable apps. In addition, it can also be seen that the security vulnerabilities of upstream suppliers' apps have a wider impact. And we have submitted more than 300 exploitable vulnerabilities in total. Among them, 38 vulnerabilities involving 15 vendors have been confirmed, and 32 CVE and CMVD vulnerability numbers have been assigned. From this, we can answer the last 2 questions. For question 3, apps with unfixed CVEs appear in almost half of vendors' room images. The affected vendors may be excessive trust in the code security of well-known suppliers. For question 4, all vendors' room images have potential security risks in the pre-installed apps. it may lead to multiple kinds of vulnerabilities. Okay, that's all. Thank you.
Very good. Thank you very much. And so one last time, do we have a speaker for an empirical study? Evidently not, so we will go directly to the discussion. You can either put your questions or comments in the chat session, or we can try to moderate them verbally. Actually, for Qinshan, I was wondering if you also did some measurements on the Apple platform.
Yeah.
So for the large scale measurements, did you only use the Android platform?
Yes, we only measurement Android vendors. Yes.
Okay.
May I ask a question?
Go ahead.
Yeah.
May I ask questions to other authors, other papers?
Other papers, not me.
Oh yeah, and other papers. Can you hear me, Nancy?
Yes.
Okay, can I ask questions to other papers regarding other papers?
Yes, absolutely.
Oh, okay. So this question is actually for Ziqi. Ziqi, you can hear me?
Yes, I can hear you.
Yeah, I think this, and thank you very much for your presentation. It's a pretty good one. And I think this is tackling a very important question about this kind of transfer learning. So I have a question regarding your like teacher-student model. You mentioned that in your workflow, because we know that the fine-tuning and the pre-training are like mostly on the same model. So by teacher and student, are you meaning the same model or different models?
In transfer learning, the student model is fine-tuned from the teacher model, and using a different data set.
Right. So this is a little bit confused me, because there's another way of teacher and student, right? I mean, the knowledge distillation, that you use large model as a teacher, and then you use a small model as a student, and then you distill the knowledge out of it. So basically, there are different models, but in your case, you're the same model, right?
Yes, in my case, it is the same model.
Oh, I see. Okay. So basically, the vulnerabilities of the networks will be directly transferred from the pre-trained model to the fine-tuning model, because they're the same.
Because they use the same model, and the student is only slightly different from the teacher.
I see. So here's the following up question, probably not related to this paper, but so currently there are like many pre-trained models, which is really large, and like the way you're showing is that the user download the model and directly fine-tune the model is probably impossible. Like, for example, I want to use like GPT-3, right? I cannot really download the model and load that into 1 or 2 GPUs. So I'm thinking probably this kind of knowledge distillation will be a future for this field, that we can create some distillation. So I'm thinking if the large model has the vulnerabilities, but the student model is distilled from the teacher's model, there are different models. Are the vulnerabilities still there, or is it possible?
I have seen some DM backdoor attack against the knowledge distillation, but I feel that in this situation, maybe the inherited backdoor is less than the directly. And I think the same case works for the adversarial vulnerability.
I see. Yeah, that makes sense. Yeah.
Yes, I think because the student is trained from scratch. Yes. Although it maybe use some feature loss in the knowledge distillation, but the difference is larger than directly reusing the teacher.
Yeah, that makes a lot of sense. Yeah, that's actually what I thought. But I don't know much about like DN testing and DN like verification, so I'm curious. Yeah, thank you very much.
Welcome.
Other questions? Comments?
Can I ask a question? Can you hear me?
Yes.
I have a question to Qinsheng Hou. How by your automatic framework are accurate? Use manual verification?
I have lost some voice.
How do you results obtained your automatic framework are accurate? Manual verification?
Yes, we have manual verification of exploitable issue vulnerabilities, but we can only do this verification on our own devices. Yeah, and indeed, we also use some script to help me do this verification, such as the I mean, oh sorry, I just forgot the tool name. Okay, yeah, we also have some open source tools to help us do this.
Yeah. Can your automatic framework be improved from the results of manual verification? I think maybe it can be learn something from the results of manual verification, right?
Yeah. Okay. Sorry, you mean?
I think we can. I think we can learn something from the results of manual verification to improve the automatic framework.
Yes. We actually yes, we have after the manual verification, we also have implement some detection features to detect the vulnerabilities. Yeah, we also develop some script. Yes.
Okay, thank you, Qinsheng.
Okay.
I have a question. We talked about inheriting flaws from code that's reused, and we also talked about third-party libraries. Is there a potential relationship between the work that was done in those two areas, because they both involve, in a sense, reusing or importing code that comes from elsewhere? So it would be Yongkang and let's see, the inheritance, Zhiki Zhang.
I feel that the problem inheritance from third party is one case of the inheritance in code reuse. The third party is a special case.
Yes, I think third-party library reuse is a more basic case of some code reusing, because we studied the binary code, which is the more close to assembly code, which is running directly in CPUs. About model reuse, they are a higher level reuse of codes.
I've always found it interesting that so many problems arise in terms of ordinary errors in reused code, and now we are seeing something of the same effects, which led me to another question. Do we have any idea of the, we hear about third-party software a lot. Do we have any idea of the extent to which reused code actually does exist and inherit vulnerabilities, or is it a theoretical case right now?
So do you mean some real cases?
Yeah.
In my presentation, I mentioned the heartbleed bug in the OpenSSL library, and I think it is a very famous case. But I currently don't think of other maybe real cases.
I know we see a lot of things in the news about attacks involving third-party libraries. I don't know that I've seen any about attacks that involved reused code, but maybe that's just because the people reporting on these things don't view that as being similar to a third party.
I have some case, real world case where third-party libraries is the issue. In our experiments, let me share my slides. Here is malware analyzing in a real world. It is a Mirai, which is you can view it as a third-party code, and the variant at 2020 is a typical scenario where the original source code or third-party code is taken apart, and the new and the variant are built just like a Trojan. It is just like a normal program in the system, and the third-party code is the only part of the software in the variant. You can the main part of the Trojan is benign, but only small part is the Mirai, which is a malware. And the detection shows that this small part reuse can lead to many issues. Here is a case, and another case is that the libpcap, which is also from another malware, and it is only small parts of the malware, and we think this is a typical case.
Thank you. And actually, going back to the beginning, I had a question about the deep learning. That is such a hot topic these days in terms of the algorithms and whether they're biased, and if vulnerabilities exist, how would we detect them? Do you see your research as just the beginning of this? It seems like there's a lot of work to do. And I wonder, having spent many years in software development, what we can do to detect those vulnerabilities before we are too far into the development process.
Right. So I can start with the first question, that like how far are we from achieving some real goals of vulnerability detection that by using the deep learning models? So actually, I've been studied on this topic for maybe 2 years, and then I can feel that the deep learning models in general is very powerful to identify a lot of data dependencies and vulnerable patterns that trigger the real security issues. But I can also feel the limitations of such kind of methods. That, for example, most of the existing works that are working on like function level vulnerability detection, or like program slicing level kind of vulnerability detection. But when we manually check some tricky cases of the vulnerabilities, actually for non-expert human, we cannot tell whether this is vulnerability or not without, a huge amount of additional information, like the traces, like the vulnerability triggering traces, and the whole project, the context. I think if for human it's very difficult, then it is probably even more harder. It is even harder for the deep learning models to learn that. So, and another limitation of deep learning models is that it cannot behave like a human, that you can click here and there to, combine the information all over the place, right? You can just click the computer and get the information you want. But the deep learning models heavily rely on whatever we feed into the model. So, and there is actually a limitation of the input for the model. So how can we comprehensively input useful knowledge with such limitations? I think it's a pretty challenging problem. Yeah.
And what about, so we've talked about vulnerability. What about malware injection?
You mean, what is the question, sorry? You mean, what about malware software?
How easy, this is, of course, is maybe both before and after the fact. So the vulnerability opens up the potential for an attack, but if a successful attack has taken place, and there was malware that's going to bias the model, are we able to detect that?
So if the malware is some kind of reported version that we all know there is a malware, it looks like this, and then we can just ask the model to retrieve such kind of code snippets out of the large out of the large code base. It is more like a code retrieval or information retrieval. You have a key of that known malware, and you just using the deep learning models to do the search. So that is a way. But if the malware is unknown and it has very tricky design to fool the human, then I think it is very difficult for the model to tell it is a malware or not.
Well, that's true. I would agree with that. That's an interesting problem, actually, that we can all contemplate. Other questions from? Let's see. We've got a number of views, a number of people participating. Questions from the audience or from one of the other speakers, or comments? Is anybody doing similar research?
I have a question for Tan Yang. Can you hear me? I have a question for Tan Yang. Yeah. I noticed for the module quality assessment design, I noticed you assume the functions with similar functionalities are likely to appear close to each other to form a community in the graph. I want to know if I want to do another work, such as grouping the statements in a function according to the semantics, such as data dependency or control dependency. I can obtain a program dependency graph. Each node is a statement, and each edge is the relationship between the statements, such as data dependency or control dependency. Do you think your method can work for this this scenario? Thank you.
Yes, I think our method is based on community detection. Your scenario is can apply to community detection algorithm also. But the question is, usually in a binary program, the connections are very dense, and hence the algorithm will be very, very slow. We do some work in our designs to decrease the density of the network and to perform the community detection quicker. Yes. In your description, I noticed that the statement you use statement as nodes, which statements will be far more than functions. Compared previous works, they are usually works in source code modelization, and they grouped the source code by files. Files is a larger, higher level conclusion of many functions, which makes their algorithm faster. And our main challenge is the efficiency. And I think your idea will face a bigger challenge in efficiency.
Okay. Thank you, Tan.
Any other questions? We are almost out of time. Or comments? If not, I would like to thank all the speakers and especially Jordan for helping me out when I was in a pinch. It's been really interesting research for me to see, and certainly overlaps some of my interests. So I'm going to be going back and rereading those papers and maybe get in touch with some of you later. Thanks very much.
Thank you, Professor.
Thank you.
Thank you, presenter.
Have a nice day.